The second skill that's important for us to think about in Chapter 3 is the concept of empirical and molecular formulas. And importantly, not just knowing conceptually what these are, but being able to determine what the empirical or molecular formula is given certain sets of data. So again, the empirical formula shows us the relative numbers of atoms in a compound. We can also think of that as the simplest whole number ratio of the atoms in a compound. Whereas the molecular formula, as the name implies, for molecules will only be for covalent compounds. But this will show us the actual number of atoms in a compound. And maybe you remember from lecture, we talked about the concept of carbohydrates. Carbohydrates were called carbohydrates because they had H2O and carbon. So the empirical formula for every carbohydrate is carbon plus H2O, 2 hydrogens and 1 oxygen. We'll see that kind of come into play in a little bit here. But again, our problems here, we have 3 problems that we'll work through. Deal with empirical formula determination, molecular formula determination, and again, using some more complex data to determine molecular formula. Remember, big picture here is that these problems are easier or harder depending on how directly the information is given to you. So you'll see that we stopped with sample problem 3.6 in our concepts of the mole, but we jump right now to problem 3.9. And that's because the first problems really deal with giving information fairly directly to you to determine empirical and molecular formulas. So we're going to kind of work on a couple of the more challenging problems that ask us to do a little bit more work to determine either empirical or molecular formulas. So sample problem 3.9 here is determining the empirical formula from masses of elements. So analysis of a sample of an ionic compound. So they tell us it's an ionic compound. So again, knowing that we have an ionic compound, our empirical formula and our molecular formula really would be synonymous, but we tend not to use the term molecular formula for ionic compounds. We really only deal with empirical formulas because ionic compounds really are simplest whole number ratios of the ions in that formula unit. So we have sodium, chlorine, and oxygen as the elements that are in this ionic compound. And again, if they didn't tell us that it was an ionic compound, hopefully when we saw that we had a metal and then 2 nonmetals, we would have known that that was an ionic compound. But we want to calculate the empirical formula. So again, giving information that we know, we are given masses of these substances. So 2.82 grams of sodium, 4.35 grams of chlorine, and 7.83 grams of oxygen. Where we want to go is we want to know the empirical formula. Again, just as a review, an empirical formula is the simplest whole number ratio of the atoms in a compound. And again, in this case, we know we have an ionic compound, okay? But it's the simplest whole number ratio of the atoms. Again, we need to think about then getting to moles. It's not the simplest whole number ratio of the masses. It's the simplest whole number ratio of the number of atoms, which again, we can directly relate to moles. So thinking about our roadmap, we need to take this information and we need to go to moles. Well, we can go from mass to moles using molar mass, okay? Once we have moles, we can take the simplest whole number ratio of those numbers of moles to get to our empirical formula. So 2.82 grams of sodium. Again, we can go using the molar mass for sodium between mass and moles, knowing that we've got 22.99 grams of sodium for 1 mole of sodium. Okay, so that's equal to 0.123 moles of sodium. Doing the same treatment for these other substances, 4.35 grams of chlorine, 1 mole of chlorine. And notice I'm not saying chloride, even though this is an ionic compound. As we'll see, this is not going to be a chloride anion. We're talking about the element, so I'm using the word chlorine. 35.45 grams of chlorine, 0.123 moles of sodium. and then 7.83 grams of oxygen. 1 mole of oxygen is 16.00 grams of oxygen. 0.489 moles of oxygen. Okay, so here's often where students don't know where to go. They know that an empirical formula is the simplest whole number ratio, but we're not given things that are whole numbers. So the question is how do you get this to whole numbers? So how do we get to whole numbers? And the solution is you divide by the smallest number. Okay, so we're going to divide everything by 0.123. Now remember, if we divide everything by the same number, that doesn't change the integrity of this ratio because we're dividing everything by the same number. So the ratio will be the same. So we're not changing the integrity of this data. We're just scaling it all by the same factors to try to get whole numbers. So again, after we divide everything by 0.123, we're going to get 1 mole of sodium. We're going to get 1 mole of chlorine, and we're going to get 3.98 moles of oxygen. So here is a time where I'm going to tell you it's okay to round. This we can round to 4. That's going to be okay. If you had something that was 3.5, we don't want to round that either up or down. If you even had something that was 3.3, that's probably not something you want to round. Rounding to a whole number is really going to be something that's pretty darn close to begin with. All right, so what this means is we have NaClO4. So this problem asks us to figure out the empirical formula. Here is the empirical formula, and it asks us to name the compound. So again, problems have levels of difficulty depending on how directly information is given to you and or how many things you have to pull in from other chapters. So part of this problem is pulling in information from chapter 2 where we have to name this compound. If you're having problems naming, go back to chapter 2 and review those sample problems. But this compound is called sodium perchlorate. Sodium perchlorate. This has the most number of oxygens, so it's the 8 and then the per in front of that. So sodium perchlorate. Again, just as a little clue as to what some of the more simple problems could be for a determination of empirical formula, what if I were to give you the moles of each of these directly? Maybe I started this problem from here. Then you just divide by the smallest whole number and you'd get to here. So problems have, again, levels of difficulty based on how directly information is given to you. This problem was a little bit more challenging than some of the earlier sample problems in this section because you had to actually walk between mass to moles and then the ratio of moles to get empirical formulas. Simpler problems give you moles directly, and you have to go here. As we'll see when we work sample problem 3.11, we have another level of difficulty where we're not even given this information directly. We have a problem where we do what's called combustion analysis to actually get this data. So that's a fairly involved problem, not one you're likely to see on a quiz, more likely on an exam. But again, this problem, kind of an intermediate level of difficulty.